Okay, so off we go. Here's where we were last time, where we left off last time. So we've talked in the past about level sets. Y'all remember what those are. And it turns out that level sets have a surprising relationship with gradients. So the way we're going to see this is by looking at a level set. Here you go. Here is a level set of some function of, well, as I have it drawn here, 3 variables, right? Just arbitrarily, so I can have a picture. And I'm going to make what I'm going to call an obvious observation. And that is that if you're on this level set, and being as the level set is defined by where the function f is constant, then it's not changing, right? I think that's a pretty obvious observation. If it's constant, then it's not changing. Or said differently, the rate of change is 0. Again, because it's not changing at all. Okay, so now with that in mind, let's think about that as applies to this following scenario. Suppose that I'm moving along a particular path that is entirely on this surface, right? So let's think about what the value of f is as I move along this path. Well, where I start, the value is c, and then a little ways further down, the value is c, and then eventually over here, still c. It's c the whole time, right? So again, not changing. So the rate of change is 0. So as I am at this point, which I am at some point on that curve, and moving with this velocity, that being literally the velocity of the path at that point on that curve, the function's not changing, right? So per unit distance as I move in that direction, function's not changing, because again, it's not changing at all. It's on the level set, and so the rate of change is 0. Okay, now let's think about what this applies to. So this applies when I'm looking at that velocity vector. What is it about that velocity vector that makes this work? Well, it's the fact that it is the velocity vector for a curve in the surface. Let me say it a little bit differently. It is tangent to a curve in the surface. Let me say that a little bit differently. It's tangent to the surface. Right? So any tangent vector to the surface is going to be the velocity vector of some curve on which the function's not changing, and so that directional derivative is 0. Okay, now what does that have to do with anything we might be interested in? And I just make the observation here that, let me clean up the mess, let's see here, I'll do this in purple. Directional derivatives are computed with dot products with the gradient. So when I say that directional derivative is 0, another way to say that is the dot product with the gradient is 0, and dot product equals 0, of course, means orthogonal. Right? So we get a surprising, sort of unexpected punchline here. We started off by making this painfully obvious observation. Look, at the function's constant, then its rate of change is 0. Well, of course. And then it's a quick little connect the dots, and now we've got this really non-obvious fact that the gradient of f is orthogonal to every tangent vector to the surface. And now I make the appeal, if your gradient vector is orthogonal to every possible tangent vector, geometric appeal. Think about all those tangent vectors. That means it's got to be orthogonal, to the tangent plane, which means it's got to be orthogonal to the level set itself. And so this is the big punchline. Let me clean up so I can write this a little bit better. We started off again with some surface that was a level set. We have now concluded that gradients and level sets are always orthogonal. That's a really cool fact. Again, very much not obvious from a geometric perspective, but a really powerful conclusion. Let's see here. Now, one important fact, subtle important fact. commonly mistaken important fact here. You got to be really careful of what function you're talking about, right? It's really easy to look at a surface and equate the surface with, the first function that kind of occurs to you, whatever function gave rise to that surface in whatever way might have just kind of happened in the question or the context, whatever it is. And of course, that's not true. When we talk about a function in relation to a surface, you got to be very particular about what kind of a construction are we talking. Are we talking about graphs? Are we talking about parameterizations? What are we doing here? Right? So, very importantly, it's the function whose level set we're talking about, whose gradient is perpendicular to that level set. Very, very important. Do not take the function whose graph is this level set. Wrong function. It's the function whose level set gave rise to that level set. Does that make sense to everybody? Okay. How's everybody doing on this result? Does that feel good? This is one of my little favorite facts about the calculus of level sets. Remember I talked a while ago about how, there's a bunch of calculus facts that we're going to see, and when we interpret calculus geometrically, you got to pay careful attention to what geometric context are we talking about. So this has got nothing immediately to do with the calculus of graphs. This is about the calculus of level sets. Okay, so let's see how we can make use of this. This calculation has a lot of little details in it, and I don't think the details rise to the level of being worth spending a lot of class time on. So I'm going to hit the highlights on this example, and I'm going to let y'all read the ensuing example that follows. It's a pretty straight read. So what we're going to do here is we're going to revisit the idea of tangent planes. And just as a reminder, we've previously understood tangent planes as being the graph of the linear approximation. That's where we first wrote down tangent planes. We started with linear approximations, which we motivated by, we feel like the linear approximation should behave a lot like the function that you're approximating, right? And then did a bunch of algebra to figure out how would you construct such a thing. Tangent plane is the graph of that. Okay, so we're going to now find the equation of the tangent plane in a completely different way, arguably a much easier way. It's pros and cons. Okay, so here's the big idea. Suppose you're looking at a graph. Right, so we've got some surface. That surface is a graph. And let's see, I tell you what, I'm gonna highlight this a different way. This surface that we're interested in, I'm gonna do it like this. In green, I'm gonna highlight that it's a graph because that is one way to look at that surface. That's the way to look at the surface that comes to us initially. And we start off knowing that it's the graph of some function little f. And then I'm gonna say, you know what? Yeah, but that surface, even though it came to us in that way, we don't have to think of it that way. I can reinterpret that as being the level set of this other function. And y'all remember this little move here, this little quick, little fast one, right? Z equals f is the same as saying z minus f equals 0. Trivial algebra, right? Hardly seems like anything happened. But the critical change, what came to us from the point of view of a graph, we now are seeing as being a level set. So, again, why do we do this sort of thing? Why do we take something that came to us as a graph and reconceive of it as being a level set? Well, because I have a calculus of level sets. In fact, we have a brand new shiny theorem in the calculus of level sets that we want to make use of. Right? And I can't use the calculus of level sets unless I literally view my surface as being a level set. And now we have. So it's basically all downhill from here. I'm going to make the observation that if you're looking at a level set, which I am, there's the function whose level set we're interested in. And just remember that gradients are perpendicular to level sets. So the gradient of G, let's see if I can fit, yeah, there you go. The gradient of G is perpendicular to the level set of G, and lo and behold, if this gradient of G is perpendicular to the level set, then it's also perpendicular to the tangent plane we're interested in, which means I can use this as a normal vector for my tangent plane, and now it's basically all over but the shouting. Yes?
So we saw that it was orthogonal, this is why we said that it was perpendicular, but if we wanted to like interpret this, like what's the interpretation, the fact that it's like the gradient is orthogonal? Like if we want to put it into words, like how would we interpret that?
I'm not exactly sure how to answer that question.
What type of valuable
let me give you just a different way to say it, right? So when I say that this vector is perpendicular to this surface, I mean, it's... what does that even mean, right? But at a given point, a surface is not that different from a plane, right? In some sense, you could take it as kind of the motivation for what we call the tangent plane, is that it's basically tracking the surface in some sense. It's kind of, oriented the same way that the surface is. And so saying that this orange vector is perpendicular to this surface means that this orange vector is perpendicular to this tangent plane to that surface. Does that help?
Yeah.
Yeah. So, we've got ourselves a normal vector. Once you have a normal vector, you plug that into the equation of a plane, right? Standard equation of a plane. You write down the normal vector. You find the point x naught. A bunch of details that y'all are going to read for yourselves. I think it's a pretty straight read. It's going to be based on this picture right here. Think through all the details. Come to office hours, of course, right? If you get stuck on any of the particulars, and be happy to help you through it. Okay, so the punchline, you'll notice, and all of this came entirely out of taking the level set point of view on that, what initially came to us as a graph. And then you're going to notice that, in fact, as we knew would be the answer, we got the graph of exactly our linear approximation that we already knew. So, old news, right? We already had this answer, but we got to this answer by way of a completely different argument. Thank you, calculus of level sets. Okay, and again, this example is pretty straight read. I think this is something that y'all can read on your own. Okay, so on to a new thing. Implicit function theorem and implicit differentiation. This first part of what I'm going to tell you about the implicit function theorem is actually something that kind of, in a way, oh gosh, it's tough, but there's an argument that says this really should have been in Calc 1 or Calc 2 courses, and it never is. And there's also a pretty good argument that it should not be, and I'll point out why. It's not really quite realistic to do this in a single variable calculus course in just a minute. But nevertheless, this, what we're about to address, concerns single variable calculus. Now here's how we're going to get started. We're going to start off with an equation of two variables. That is going to be some sort of a curve in the plane, because there's two variables. And let me start by asking the wrong question, just to keep it distinct from the right question. The wrong question is, can I view this level set as being a graph? And the answer is a perfectly obvious no. Look at that. It fails the vertical line test, right? Crash and burn. Definitely not a graph. Game over. Okay, what's the right question? The right question, very similar sounding, very importantly different, is can part of this curve, if I view only locally, if I look only nearby a single particular point on this curve. So, for example, let's think about this point right here. And by locally, I mean let's just look at some neighborhood, some conveniently small neighborhood like that. And if I look only at that part of the curve, when I say only that part of the curve, that means that I do not care about any of this stuff over here, nor do I care about any of wherever else the curve might go off to after, outside of that yellow neighborhood. This is what we mean by locally. So having this new perspective of what we mean by locally on that part of the curve, can I view y as being a function of x? And yeah, absolutely, no problem. Look at that, it passes the vertical line test, no problem. Right? We are completely absolved of any responsibility for bad things that happen way over here, because this isn't locally. We're interested only nearby this point. How are we doing? Does everybody see the question so far? Right, so locally near that point, we're good. Now, here's a tricky one. Tricky variation. What about at this point? Can I locally view y as being a function of x? And it's tempting to say, nah, look at that vertical line, we got a problem. But just keep in mind, locally means, again, we get to pick this ball however small we need to make it. We get to make it as small as we need to make it. If there's any way to make that ball small enough for the answer to be yes, then that's how small we're going to make it. Right? So if I choose the ball like that, then locally means we're only looking at this little piece of the curve. And that passes the vertical line test. Because again, we have no responsibilities at all for any of the rest of the curve like that. So the answer, locally can y be viewed as a function of x? Here the answer is yes. Okay, so what's the actual problem here? When would we ever get a no? And the no would come at a point like this. Look at that point right there. In particular, that is the point at which the curve, at that exact point, that's where the curve is kind of wrapping under itself, if you will. And I claim that the answer here is just going to be no. Because let's restrict our attention just locally. So and again, all I have to do is look inside of this little yellow ball here. All I have to do is look at this, color choices, this piece of the curve here like that. And no matter how small this yellow ball is, that little piece of curve is going to fail the vertical line test. There's no getting around it. Everybody see what I'm talking about? Okay, yes?
Could we switch x and y?
Yeah, that's a great question. Yes, absolutely. That would be a completely different question. Yeah, so here I want to talk about can y, specifically y, can that be viewed as a function of x? But you can ask the perpendicular? Yeah, perpendicular question. Can I locally view x as a function of y? And at this point, the answer would be yes. Absolutely. Yeah, but it is a different question. Okay. All right, now why would we care about such a thing? Why would what's the point of looking, say, here and wanting to talk about just a little bitty piece of curve? And the answer is, I might want to talk about the tangent line. I might want to understand that tangent line by way of it being, the slope is the derivative. But wait a minute, you can only talk about derivatives of functions, right? So I can talk about the slope of this tangent line as being dy dx, right? In other words, locally I can view y as being a function of x. Who cares that I'm not looking at this part of the curve, right? If I'm only interested in this tangent line, at that point, I only need just enough curve to be able to, in fact, define what I mean by tangent line, right? And on that little bit of curve, I just need to know that y is actually a function. So I can talk about the derivative of that function. Because we can only take derivatives of functions. You can't take a derivative of a table. You can't take a derivative of a bicycle. You can't take a derivative of anything except for a function. Right? So that's what we're getting at here. So if you were to say, hey, I'd really like to understand the slope of that tangent line, and then you're going to want to talk about dy dx. And I'm like, whoa, what do you mean dy dx? Here's the piece of curve you're talking about. That's straight up not the graph of anything. Y is not a function at that point. It's not even locally a function of x. So I can't even talk about the derivative of it. We only talk about derivatives of functions. Okay, so how a lot of high schools address this, unfortunately, is to just kind of assume that, that y is a function of x, and they just start going around taking derivatives of things as if you can, as if that's not nonsensical garbage. And then if something bad happens, they're like, ooh, hey, something bad happened. Oh, well, I guess we must have, okay, I guess that, and then they make some interpretation from it. Like, that's okay. Okay? They've got, half a page of meaningless nonsense, and then at the end, they're like, whoopsie, everything we wrote was meaningless nonsense. You can't do that, right? That's not how math is done. You need to know that what you're writing down is meaningful before you write it down. Okay. All right. So the point here is not that you can't compute the derivative at that point. That's not the point that I'm making. My point is that there is no such thing as a derivative. It's not that you can't answer the question. It's that you can't ask the question. Important distinction. Okay. All right. So how are we going to resolve this? There's a really, I think, persuasive argument that you can make. It goes like this. Here's, by the way, what it looks like if the answer is no. Let me try to do a better job of highlighting that there. If the answer is no, if y is not locally a function, it looks kind of like this. The function's wrapping under itself. Geometric appeal. This is the problem that we're worried about, right? And now, related, I appeal again that means it has a vertical tangent line. Now you're going to be tempted. Instead of calling this a vertical tangent line, you're going to be tempted to say, oh, the derivative is infinity. Right? Or then you might correct yourself. I meant the derivative is undefined. And no, it's worse than that. It's that the derivative, there is no such thing as the derivative. That's really the issue, right? So we can't make any reference to a derivative here, but very conveniently we can just observe, okay, well the problem then comes when you have a vertical tangent line. And now a reminder, gradients are always perpendicular to tangent lines of level sets, and do keep in mind this curve is a level set, right? The whole way we started this was f equals a constant was our equation. And don't forget that the gradient is partial of f with respect to x, partial of f with respect to y. So saying that is horizontal means that the vertical part of it is 0. Okay, so all together then, right? There's quite a connect the dots here. If we have a problem, then the y partial will be 0. So let me get rid of all of the mess here, and then we'll rewrite. Problem means the y partial is 0, and then here comes that contrapositive that I like, and that I'll be using quite a bit here and there throughout the course. Right? Important construction to be aware of. The contrapositive of problem implies 0 is not 0 means no problem. And this is what we can actually do something with. This is a simple little algebraic test, right? I'm going to take the function whose level set I'm interested in. I'm going to take that function, I'm going to compute the y partial, I'm going to look and see if I got 0 or not, and if I didn't get 0, I'm going to declare all is well and good, and we can proceed taking derivatives because it is a function. You can totally talk about all is good, go ahead, compute however you like. Everybody happy? All right. So why don't they do this in single variable calculus classes? Well, because it involves gradients and partial derivatives. But there is a different way around this, but the only other, I'm going to say, intuitively satisfying way around this that I am aware of still involves taking partial derivatives. Certainly the punchline involves a partial derivative. So, okay, true, to be fair, we really can't do this in a single variable calculus class. But it remains that we've got this problem, right? And it would make me happier if they would at least doff the cap and say, there's some issues here, and it turns out that you got to worry about certain cases. Look forward to seeing the answer to that in your next multivariable calculus class. But for the moment, and then they can go on and do their single variable stuff. But they never do. Okay, here's a three-dimensional version of it. Oh yeah, question.
If the partial derivative of y, like with respect to y, is 0, does that tell us anything about it?
That's a great question. It actually does not. If the y partial is equal to 0, roughly speaking, there's two possibilities. If we were to say, hey, let's assume the y partial is 0, right? Then it's possible it could look like this, in which case it's not locally a function, but it also could, okay, here's a test of my art skills. It could look like this, in which case, even though there's a vertical tangent line, it actually passes the vertical line test. Right? So yeah, so this is a one-way theorem. It's one way the good way, right? It's one way in the direction that gives us the good news that we want, and it applies most of the time, because what are the odds that it would be exactly 0? That's the relatively rare case. But yeah, great question. It actually, we learn nothing. When this y partial is 0, we draw no conclusion. Yeah. Okay. All right. Okay, so the three-dimensional version, it's actually quite similar. And first of all, let's try to identify what we're talking about here. And so you'll notice we start with a level set. Equation of three variables. Some function capital F is a constant. Let's entertain a particular point. I'm going to say maybe a point about right there. Let's think locally. Locally means I'm going to look just sort of nearby. That means that I'll be looking at just this piece of the surface. Forget about the whole rest of the surface, looking just at this little green surface, which, is oriented about like my hand is here. Does that pass the vertical line test? Yep. All good. No problem. I'm not responsible for what's going on down here. I'm interested only locally. So, yeah, all good at that point. All good at most of those points. And just like in the single variable case, the problem is when you're looking at a point where at exactly that point the surface is wrapping under itself. And if that's where the wrapping under is happening, right? Let's see here. If it's wrapping under exactly at that point, just right there, then your little piece of surface is going to be like this, and you're going to fail the vertical line test no matter what. Okay, so the wrapping under is the problem. Wrapping under, of course, would mean we have a vertical tangent plane. Vertical tangent plane means we have a horizontal gradient. Very similar argument what we just discussed. Give me 2 seconds. And horizontal gradient, keep in mind, this gradient, right, is the partials with respect to x, y, and z. Horizontal means the third coordinate is 0, and that means that the z partial would be 0. Yeah, question?
How are we failing the vertical line test on the other point over here when you did this?
This point over here?
No, right over here.
How would we fail the vertical line test? Yeah, so if the surface is like this, right, and you imagine a vertical line coming down, it's going to hit here, but then it's also going to hit here.
I meant the outermost point.
You talking about this point right here?
Yes.
Yeah, that's what I'm talking about. Yeah. So the point is, at that point, if you look at any neighborhood, that neighborhood will wrap under itself also. And so, yeah, it's just going to fail. Yeah. Okay. Nice, similar punchline. So now there's a pattern here. Let me point out what the pattern is. And again, I'm not going to prove stuff rigorously here. I just want to be persuasive, and I hope the following is persuasive. Notice whichever variable it is that you want to decide if it is or isn't locally a function, whichever variable that is. That's the one whose partial you have to take and confirm is not 0. Right, so in this example, we were looking to see if y could be viewed locally as a function. So we take the partial with respect to y, as it turns out. And then you look at this three-dimensional example. Now here it was z that we were asking, can I view z as being a function? And check it out. It's the partial with respect to z that I have to look at to see if it is or isn't 0. So that's the pattern. I claim that pattern holds, and that gives us this big theorem here. Oh, yeah, question?
Can you turn that one more time?
Do I know?
Oh, the z partial will be 0.
I'm not. Are you? I didn't get the question. I'm sorry.
Could you explain again the logic behind why the z partial is 0?
Okay, so let me just hit the highlights. So the problem, right? So we want to identify first a case of a problem and see what that gives us. The problem is that the surface is wrapping under itself. Wrapping under means you have a vertical tangent plane. Vertical tangent plane means you have a horizontal gradient, and that means that partial is 0 because this is the third coordinate of that gradient. Yeah. Right. Okay. So the general version of the theorem. If you have any level set, note this could be any dimension, right? Any level set of a function called capital F. Oh, you know what? Irregularity. We do need a capital F to be continuously differentiable. Whatever. Level set. If you want to view one of those variables, right? Notice this is in fact one of those variables. If you want to view one of those variables locally as being a function of the others, whichever variable that you want to view as a function, that's the one that you need to take the partial with respect to and confirm that it's not 0. Everybody good? That's the pattern. Now let me color code this just a little bit differently. The variable that you want to be a function is what you take the partial with respect to. The function whose level set you're looking at is what you take the partial of. Yeah.
So if it's going from R of n to R, do we have unclosed surfaces only?
Do what now?
We're only working with unclosed surfaces?
No comment. So for any C1 function, any continuously differentiable function, you're looking at its level set, and at whatever point you're interested in, you want to find out if you can locally view one variable as a function of the other. Yeah, no comment on what this surface looks like, and in fact, very often we won't even know what this surface looks like. Yeah, that's right. Yes.
Did you say C1 stands for continuously differentiable?
That's right. So So remember, this notation, C means continuous. The superscript tells you how many derivatives in addition to the original function must also be continuous. So this C1 means the function and its first derivative, first derivatives, plural, all have to exist and be continuous. Yeah, so coincidentally, a nice little fact to remember, C1 means continuously differentiable. Okay. All right, let's see an example. Here's an equation. What does that look like? Oh my gosh, I have no idea. We don't have tools. I see there's cubes in there. This is going to be weird. I don't know what that thing looks like. Right. Okay, so fine, but we can still ask the question. Look, there's a point that's on that surface, and look, maybe I'm interested in what's going on at that point, and I would like to take a derivative. Specifically, I'd like to take a derivative of x with respect to something. Fingers crossed that x actually is a function of y and z, in which case I can even talk about the derivatives, right? Well, can I or can't I? Right? So is x locally a function of y and z? And so again, reminder, whatever is the variable that you want to view as a function, that's what you take the partial with respect to. Whatever you're looking at a level set of is what you take the partial of with respect to that variable. And then punch it up, see if you get 0. Of course, you're going to plug in, the point in question. Here we're interested in what's happening at the point 1, 2, 3. So we plug in 1, 2, 3. And not 0, whoops, wrong color. Not 0, so no problem. Everybody all right? Okay. Next natural question. We know how to tell when, well, at least most of the time, we know how to tell when, let's say, x is a function of the other variables. Cool. That means I can talk about the partial of x with respect to y or z. How would I compute this? Right? Now, there's different approaches that you can take and different arguments that you can make. I think there's two primary choices, and one of them is a lot more confusing than the other. I'm going to show you all the one that I think is less confusing, the one I think is functionally easiest. Okay? And bad news, good news. The bad news is that a really full and careful dot your I's, cross your T's approach to answering that question is a hairy mess that I don't want to mess with, and I don't think y'all do either. But you may. I encourage you to look at this. Right? Okay, but the good news is that there is a streamlined alternative that does everything that we're going to really need it to do. Now, I'm going to confess right off the bat, right, that look at this diagram that I've got here. Does this diagram follow my rules? Nope. As written here, this is not written as a composition of multivariable functions. I cannot talk about the chain rule. It just doesn't work, right? It's no fair. Doesn't follow the rules. That said, I claim that this, you're just going to have to take my word for it, that is just an abbreviated equivalent of this in this case. Don't worry about the why. Take my word for it. Right? If you want to see the full discussion, come to office hours. Happy to do it. But again, I think it's not a good time investment. So I'm going to just assert that this is our picture. And let me just remind you, that means, again, we're looking at f being a function of all these variables. Of course, the whole point to f is that we're looking at a level set of it, so it is constant. So f doesn't change. That means the derivative of f has to be 0 altogether. Right? It doesn't change. And then within that constraint, we've also got that xi is a function of the other variables. Now, I'm going to try to represent it being a function of the other variables. And again, this again just terribly violates my rules. But the big idea is that it's a function of all the others. Now, if I'm going to take a partial with respect to xj, now think about how partial derivatives work. The very first thing you do when you take a partial derivative is you hold all the other variables constant. So I'm taking the partial of xi with respect to xj, and that means that all of these variables are constant. And let's see here. There's some variables in here that are constant. All these variables here, all constant. So we're going to ignore most of the variables. That are all the ... variables, constant. Okay. So with that in mind, now let's think about what happens if I fiddle with xj. Right? If I change the value of xj, what happens? And forget about compositions and matrices. Let's just think from the point of view of paths and how changes propagate through paths. When you change xj, well, on the one hand, let's see here, colors. I'll use purple. Xj will contribute directly to how capital F changes. After all, it's one of the input variables for capital F. You change xj, that's going to contribute to a change in f. But here's another thing. We're taking that, let's see here, another color choice, that xi is a function of xj. That means as xj changes, xi will change, and as xi changes, that will contribute to a change in capital F as well. And it gives you this term. And keep in mind, the whole point of all of this is that F is a constant. That means it's not going to actually change at all. That means that the total contribution of all these changes has to be 0. Yeah.
So this might sound wrong, but if you're taking the derivative of f,
yeah,
and it's a constant, and then the derivative is 0, then you're multiplying by 0 and you're adding 0 to get 0?
No, I hear where you're coming from. Right?
Okay.
So what we've got is there's a, you got to keep a couple of things distinct. So when I say that f is constant, I don't mean that the formula for capital F is literally capital F equals 6, and that's the formula, right? What it means is, let's take a three-dimensional case, right? Remember, a level set then of a function of 3 variables is a surface. So when I say f equals a constant, what I mean is we're only interested in what's happening on that surface where f is a constant, right? Now when I say, though, partial of f with respect to xj, now again, here's my surface. When I say partial of f with respect to xj, that means go in the xj direction. That's going to pull me off of my surface, right? So for the purposes of this partial, f is not constant. F is some formula. And there's going to be a non-trivial partial derivative. And likewise, the partial of f with respect to xi, that's going to have, again, here's my surface. That's going to have me going, let's say, that way. It pulls me off of my surface. The idea is that while this is non-zero and that's non-zero, altogether, we're supposed to stay on the surface. And so however this and that might cause f to change, this needs to be whatever it needs to be to make us actually stay on the surface and to make this total derivative 0. Is that cool? Yeah, it's a great question. There's a lot. That's a very subtle point. It is very confusing. Absolutely. Okay. All right. Now, of course, the whole reason for this is that we wanted to know, how do I take this partial derivative? So you solve for it and you get this formula. And boom, plug and chug at this point. Now, there are some sticky wickets and a couple of warnings and strategic considerations that I want y'all to bear in mind when you're taking tests and stuff like that. But pretty much, plug and chug example will follow. Okay, so let me give you the warnings. Let's see here. Looking at this formula. A lot of people make the following observation. By the way, this observation I'm about to give you is complete garbage, right? So don't buy into it, right? But nevertheless, this is the observation a lot of people make, and they're like, "Oh, hey, check it out, partial f and partial f," and so we cancel those, right? And then you look at the partial xj here. That's in the denominator of my numerator, otherwise known as the denominator. And let's look at this partial xi right there. That's in the denominator of the denominator. That's the numerator. Oh my gosh, this seems to work except for this minus sign here. And so as the nonsensical reasoning goes, students figure, oh yeah, I don't need that minus sign, and they throw that away. Right? Because look at the cancellation, and remember how fractions work and stuff like that. Okay, so again, garbage, right? So let me remind you why this is garbage. This is very unfortunate notation. It makes it look like a fraction. It is not. All right? That's notation that describes a scenario that has a certain premise, in which case certain things happen, and yes, among many other things that happen, yes, f changes. But this is a completely different scenario. and how much f changes in that scenario, unrelated. These two things, here and here, those are just not the same thing. You absolutely cannot cancel them. That is nonsense. Okay, so don't fall for this. That's a very common mistake to make. And here's the really important thing to keep in mind. This minus sign then, this minus sign is the only thing to distinguish the perfectly valid formula, which, if written by a student, would communicate, or at least would leave the presumption that the student understands what's going on, from this, which is complete nonsensical garbage that would seemingly betray no actual understanding, no valid understanding of how implicit differentiation works. That one minus sign is the only distinction, right? Okay, so that makes it super important. And this is just an unavoidable strategic reality. If you put that minus sign in there, then yeah, cool, good. That student knows, all signs point anyway toward that student actually understanding. And if you forget the minus sign, right? If you just kind of whoopsie the minus sign, the student who writes that down absolutely does not know how it works. And it almost looks like this student might actually believe that these are the same and that you can cancel them, and that's just, oh my gosh, it's absolute garbage, right? So it's very, very important from a strategic point of view. Y'all are all trying to impress the grader, right, with how much you understand of what's going on. That minus sign is kind of the only way to distinguish yourself from this nonsense. So it's just unavoidably, strategically very, very important. Please, 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 please make sure to remember that. Please do not forget that minus sign. I hope that makes sense to everybody. Let me pause for questions. Is that all? Good. In fact, I would make the case that the very first thing you do when you have a question where you're going to use the implicit differentiation formula that I have here, step 1, write that down. Step 2, start thinking about, oh, wait a minute, what are the other things I'm supposed to compute, and trying to think about the roles that the different variables are playing, whatever. But get that minus sign written down first. Okay. Again, it's one of these things that the more I dwell on it, the less it happens, and I'm looking forward to eventually getting down to 0. We're not there yet, but hopefully soon. All right, let's see an example. So y'all are going to recognize this equation. This is the exact equation we were looking at in the previous example. And again, we're looking at the point on this surface, whatever that thing is. We're looking at that point right there, and we've already established that x is locally a function of y and z. And because x is locally a function, we could reasonably ask the question, what is its partial with respect to z? Okay, so let's see here. You want to compute that partial like this. Write down that minus sign first. Don't leave yourself open to the possibility of getting distracted by other things and then forgetting that minus sign. Get that minus sign on the page. Right? Now, what comes next? We have a problem here. This scenario, the variables are called x, y, and z. In this scenario, the variables are called something different. The formula that we have here involves variables that don't look like our variables. What are we going to do about this? Right? How do you keep it straight? And I have a simple solution to that, and that is, again, step 1, don't forget the minus sign. Step 2, remember all that nonsense about canceling differentials? Sure was easy to remember, sure was except for that minus sign, it gives you the right answer. I use that as the memory trick, right? So, we're going to have the fraction of two different partials of f, and and the variable that is in sort of the numerator of what you're looking for is the denominator of the denominator, and the one that's in the denominator is in the denominator of the numerator. Just like fractions work, that helps you keep it straight. And then look at how this works out very nicely. That goes there, and oh gosh, with the colors, that goes there. You compute some partials, you plug in a point, and the thing we're interested in is easily computed. Okay, let's see. Are we out of time? Yeah, I'm out of time. Okay, I have one more quick thing to say. I'll say it on Wednesday. Y'all have a good day. See you later.